In this lecture, let us discuss about transformers, which is a deep learning model, and it is designed for sequence to sequence tasks like machine translation, text summarization, text generation, okay, etc. Unlike earlier models such as RNNs and LSTMs, transformers rely entirely on self-attention mechanism in order to process input data in parallel, making them highly efficient and scalable. Then coming to the overview of the transformer model. So first coming to the encoder decoder architecture of transformer follows an encoder decoder structure where this encoder processes the input sequence and converts it into meaningful representation. Whereas the decoder part, it uses these representations which were generated by the encoder in order to generate output sequence step by step. Then coming to the encoder processing part. So this encoder consists of multiple layers that apply self-attention, that is multi-head attention mechanism and feed-forward networks in order to extract important information from the input sequence instead of recurrence, which is used in RNNs or LSTMs. Then decoder functionality. So what this decoder does, so it will generate the output sequence based on the encoder encoder's processed information. At the same time, it also uses masked self-attention in order to ensure predictions are generated one step at a time without looking at the future words. And here we'll be using this positional encoding in order to retain word order information. Then coming to the architecture part. So this is the diagram or architecture of the transformer. And here you can see this is the encoder part and this is the decoder part. So this encoder, it will process the input sequence and generates a meaningful representation that captures its meaning. And it consists of n layers, each containing multi-head attention, then feed forward network, and add and normalization part. Okay. So this encoder contain all these three components. And the input passes through this input embedding. So you can see the input part as well as positional encoding before entering the encoder. Then moving on to the decoder part, which is present at the right side of your diagram, this one. So the decoder takes the encoder's output and generate target sequence. So again, it also consists of n layers. So you can see the number of layers n, each containing masked multi-head attention, then multi-head attention, feed forward network, add and normalization layers. So decoder receives the output embedding as well as positional encoding just like encoder. So finally, decoder produces the output probabilities through a linear layer followed by softmax activation function determining the predicted word at every step. So this structure forms the basis of models like BERT, GPT, and T5 models. And coming to the components we saw in the diagram, first input embedding, it converts input tokens or words into dense vector representation. Each word in the input is represented as a high dimensional vector. Say, for example, you want to translate a sentence, hello, how are you, into French. That is English to French. So, here the words are first embedded into numerical vectors in the first component. Then, coming to the positional encoding part. So, since these transformers they do not process words sequentially like RNNs, we add these positional encodings in order to retain word order information. Yes. So positional encodings, they are sine and cosine functions that add unique signal to each word position. Say I'll tell you in the example how these sine and cosine functions are added. Then coming to the multi-head attention encoder part. So the encoder contains this multi-head self-attention layers, and self-attention allows the model to focus on relevant words in sequence. So it uses terms like query, key, value in order to calculate attention. So again, there is a formula for this. So if you take the same example, sorry, if you take another example like the cat sat on the mat. When processing the word sat, model attends cat and also on. Okay, that is the previous word as well as next word. The cat sat on. So if sat is at the middle, previous word is cat and next word is sat. Next word is on for this word sat. So model will attend both the words because they provide useful context. Then coming to add and normalization, this is residual connection. So skip connections or residual connections help the model train faster and avoid vanishing gradients. And also layer normalization ensures stable training. So example, if an attention layer modifies an input too much, residual connections help retain some of the original signals. Then a feed forward network. A fully connected feed forward network is applied after self attention mechanism, which consists of two layers with an activation function. So the activation function used here is ReLU. Next one is encoder stacking, which is a collection of n layers. In the diagram, you can see this is the encoder part, right? So it contains multiple identical layers nx times. So here each layer contains multi-head attention, feed forward network, and add and normalization parts. So more layers mean better feature extraction. Say a 6-layer encoder can learn deep contextual meaning. Then we have decoder, which is present at the right side of the diagram. The decoder, it also consists of nx layers. Okay, so n here you can have n number of layers, and the decoder receives output embeddings and generate predictions from that, the probabilities. So if in translating the sentence the cat sat to French, decoder gets some translated sentence for that. Then coming to masked multi-head attention. So unlike the encoder, decoder has masked attention mechanism which prevents attending to future words and also ensures the model only sees previous words during training part. Then multi-head attention, encoder decoder attention part, this one. So this layer allows the decoder to focus on important words from the input sequence. So here this uses encoder outputs as keys and values and decoder hidden states as queries. And then final feed forward and softmax. Encoder outputs go through the linear layer. So you can see that this is the encoder output which goes through the linear layer. And the softmax activation here, it converts them into probabilities over the vocabulary. Let us see all these components in detail with an example. So first we are taking step 1, that is input embedding. Here we need to convert the given words into word indices. So each word in the vocabulary is mapped into a unique index. Say the given words in a sentence are I love AI. So for every word we gave index value. So we are just assuming that we have a vocabulary like this, and these are the corresponding index values. Then step 2, convert the word indices into embedding vectors. So here this word embedding matrix, it maps each word into a dense vector of size D model. So usually in transformer model, this D model value will be either 512 or 768. So we are assuming D model value as 4. So that is total number of columns for every word as 4. So this is the size of a vector. Okay. We are taking it as 4 for simplicity, and the embedding matrix will look something like this. So these are the word embeddings for every word, and this is the corresponding input embedding matrix we got. So as the total number of dimensions are considered as 4, we got total 4 columns. And as we have 3 words in the vocabulary, these are the word embeddings for every input word. That is I love. Then step 2 is positional encoding. Transformers, unlike recurrent neural networks, do not process input sequentially, right? So instead what they'll do, they process the entire sequence simultaneously, which makes them efficient. But this makes a problem because here we need to consider how the model understand word order. If everything is processed, if the entire sequence is processed simultaneously, how the model will understand word order. So that's a problem. So since these transformers do not have built-in sequential processing, we need to add positional information manually. So that is nothing but positional encoding. So we can say that this is a technique that adds unique numerical representations to words in a sentence based on their position. This actually helps the transformer model understand the order of words in the sequence. And after that, we need to combine the word embedding as well as positional encoding in order to get the input representation. Okay, let us see this thing here. So first thing is convert the word into word embeddings. So take the words I love AI. So we are converting it into dense vector representations or word embeddings. So these are the embeddings we got for every word. So that's what we saw here, right? This is the input embedding matrix. Then assume that our dimension is 4. Then compute positional encoding values. So you can get that by using these two formulas. So transformer uses sine and cosine functions in order to generate positional encodings. So you can see that position, it is nothing but position of the word in the sequence. Then we have D model, that is total embedding dimension. Here for simplicity, we are assuming this value as 4. Usually it can be 512. Then I value. So this I value is the index of the embedding dimension. Then even indices use sine function. So you can see this 2i. So even part or even indices use sine function, whereas odd indices 2i plus 1 use cosine function. And the denominator, this 10,000, is a scaling factor that ensures different frequencies. Okay, so let us just substitute values here. So for position 0 and so for if the position value is 0 and index value is 0, so you'll get 0 comma 0. Then sine of position is 0 divided by 10,000 power 2i. Okay, 2 into 0, that is 0 divided by d model. So this is 0 by d model value is assumed as 4. So we'll get sine 0 value. Now take for position 0 cosine value. So if this value is 0, then you'll get 2 into 0 plus index also 0, right? So 2 into 0 plus 1 will get 1. So position will be 0 comma 1. Similarly, just like how we substituted values in the previous case, you will do the same here. So here actually we need to consider 2i plus 1. So we'll get 1 divided by 4. So this is a cos value. Then for the position 0 comma 2, again sine part. So 2 into 1, I value 1 this time. So 2 into 1 is 2. So 0 comma 2 will get this value for sine. Then coming to the cos, here I value, if this is 1, you'll get 2 plus 1, 3. And this is the result. Okay, so this is for position 0. So positional encoding for word I is, we got these values for this I. So how it looks in the matrix? So we have embedding matrix like this. So this is 0, 0, 0, 1, 0, 2, 0, 3. This is for the word I. Okay. So in the same way, we need to find out for love and AI also. So for position 1, you can do the same thing in order to get the second row. So 1, 0, 1, 1, 1, 2, and 1, 3. So this part 1, 0, 1, 1, 1, 2, 1, 3. Then 2, 0, 2, 1, 2, 2, 2, 3. So in that way, we are getting the complete embedding matrix for all the 3 words. This is positional encoding part. So this is for position 2. We'll use the same approach. And then we need to add word embeddings as well as positional encoding values. So if you take the I for position 0, you'll get, we got the word embedding values like this. So these are the word embeddings 0.1, 3, 7, and 2. Okay. Then positional encodings which we got are, these are the encodings we got for the word I at position 0. So this is the final input representation. So how we'll get this final input representation? By adding word embeddings plus positional encoding. So 0.1 plus 0, we'll get 0.1. 0.3 plus 1, that is 1.3. 0.7 plus 0, 0.7. 0.2 plus 1, 1.2. Right? Then similarly for word love, these are the word embeddings and these are the positional encodings from which we got final input representation after adding these two embeddings. And we do the same for word AI also. This is a final input representation. So after doing all the things, after positional encoding, this is the final input representation. These are the values we got, right? 0.1, 1.3, 0.7, 1.2. And for love, 1.3, 1.1, 0.9, 1.5. For AI, 1.7, 1.0, 0.3, 1.8. So this is the final input representation for the sentence, I love AI. And after this, we need to pass it to the transformer encoder. So you can see all these things in the diagram clearly. So after adding element-wise sum, so after adding positional encoding with the input embedding, we need to pass this value to the encoder. So this is the encoder part. Yes. The final input vectors go into the multi-head attention mechanism present inside the encoder. And each word now has word meaning, that is a word embedding as well as position information.